Okay, welcome to learnathome.ng. We are sorry for that short delay. So today our topic is capacitor and capacitance, and then we'll be looking at the following objectives. So we are going to start with the introduction, then we are going to move to the performance objective, then we take a look at the lesson discussion for today. Then we take a short break, we come back to take your question and answer, and then we close session. So for today, as I said earlier, the topic is capacitor and capacitance. We'll be covering the following objectives. We are going to learn to define capacitor, and we are going to state the components of the capacitor. Then we are also going to explain the capacitance of the capacitor. Then we are going to look at factors affecting the capacitance of a capacitor. Then we are going to learn to calculate series arrangement and parallel arrangement of capacitors. Then we close the session with the energy stored in a capacitor. But before we start, we have an announcement for today. So today's class will be a little bit different from other classes, because today we are going to be rewarding our viewers, and the criteria for the criteria we are going to use are going to be: 1, you have to stay online through the whole lesson. 2, you have to ask constructive questions during the lesson. And then lastly, you actively answer the teacher's question. So if you can do all these 3, then you are going to be part of our winners today. So let's just dive in straight to what we have for today. So what is a capacitor? So a capacitor is a device for storing electric charges. Simply put, it's a device for storing electric charges. And it has a symbol of this. As you can see, we have 2 vertical lines which represent the 2 plates, metal plates, or we call them conductors. So those 2 lines represent the metal plates or conductors. And then in between, we have a material called a dielectric material. A dielectric material, which is an insulator. So as you can see, the components of a capacitor include: 1, we have 2 metal plates which serve as conductors, and then we have a material sandwiched between the 2 metal plates which acts as an insulator and is called a dielectric material. So at times questions would ask you that what is a dielectric material? So a dielectric material is just an insulator placed in between the plates of a capacitor. So these are the 2 major components of a capacitor. We have the metallic plates which serve as conductors, and we have the dielectric material. So let's look at the capacitance of a capacitor. But before we move further, let's just write, as we progress, let's write what we've learned. Okay, so the capacitance of a capacitor now. So the capacitance of a capacitor is the ratio of the charge across the plates. The charge across the plate is denoted as Q, has a value of Q, to the potential difference across the plates, V. And we can deduce that from there that C is equal to QV. So if you are told to define the capacitance is just the ratio of the charge across the plates, which is represented as Q, divided by the potential difference across the plates, which is represented as V. So simply put, C, the capacitance, is equal to Q divided by V. And from here we have that Q is equal to what? CV. Our Q is measured in coulombs. Our capacitance is measured in farads. Don't forget that. And then the potential difference is measured in what? Is measured in volts. But most times we don't give the unit for capacitance in what? In farad. We give them subunits for the capacitance of a capacitor. And the subunits are, it can be given as 1 microfarad. So whenever you see a microfarad, it is represented as 10 to the power of -6 farad. So micro, this symbol is a Greek symbol. which is sounded as mu. It's called microfarad, and it's equal to 10 to the power of minus 6 farad. And then we also have 1 nanofarad, which is 10 to the power of minus 9 F. And then we have 1 picofarad, which is equal to 10 to the power of minus 12 farad. But this one here is the most used. So let's add it to. So we said 1 microfarad is equal to 10 to the power of minus 6 farad. So let's take a look at factors affecting the capacitance of a capacitor. So what are the factors affecting the capacitance of a capacitor? Basically, we have 3 factors affecting the capacitance of a capacitor. The first one is the nature of the plate. Nature of the plate. Don't forget that I said that a capacitor has two metal plates. Has 2 metal plates. And those plates can be made up of different material, that's conducting materials. So the nature of the plates, that is the type of the conductor we are using, affects the capacitance of the capacitor. Another factor is the area of the plate. Area of the plate. Let me just draw below here. So the area of this plate here, the area of this plate also affects the capacitance of the capacitor. Let's assume this is what? A. The area of the plate is denoted as what? As A. So what effect will it have to the capacitance? We say that C is directly proportional to what? To A. C is directly proportional to A. That means that as the area increases, the capacitance would also increase. And as the area reduces, the capacitance would also reduce. So simply put, whatever happens to the area also happens to the capacitance. And the third one, we have the distance between the plates. Distance between the plates. And we are going to represent that as what? As D. So if these are our plates, so this is the area, and this space here is the distance D between the plates. So how does the distance between the plates affect the capacitance? So we say that the capacitance is inversely proportional to the distance between the plates. So what that means is that as the distance between the plates reduces, so does the capacitance, the reverse happens to the capacitance. So if the distance increases, the capacitance would reduce. And if the distance reduces, the capacitance would increase. Don't forget what I said there for area of the plate. I said it is directly proportional to capacitance, which means that as the area increases, the capacitance would also increase. And as the area reduces, the capacitance would also reduce. But for distance, the reverse happens. As distance increases, the capacitance would reduce. So there are lots of questions on these factors in WAEC. At times they just ask you that what happens to the capacitance if the area of the plate is reduced, or if the distance of the plate is increased. So if the distance of the plate is increased, then the capacitance would reduce. Don't forget, the reverse happens. But if the area is reduced, the capacitance would also reduce. So just stick with us, stick with me. I'm going to give you questions related to this in the WAEC past question. So I said that C is proportional to A, and C is inversely proportional to what? To D. So when we combine all these parameters together, we say that C is proportional to A, and we say that C is inversely proportional to D. It now brings us to an important formula, which says that the capacitance is equal to the permittivity of the material times A divided by what? By D. where all the letters represent their normal symbol. C is the capacitance. E is a constant called permittivity. Is a constant called permittivity. A is the area of the plate. And D is the distance between the plates. It's the distance between the plates. Yeah, so that's an important formula in physics. C is equals to permittivity times area divided by D. And the question on this topic has been coming out for the past 4 or 5 years now. WIC has been repeating questions on this topic. 2017, they even brought out a question in the theory section that relates to this formula. We are going to treat all those questions. Just stick with me. So I said that C is equal to what? EA over what? Over D. So let's move forward. But before I move to arrangements of capacitors, let's take a look at the key things we've talked about. So we started with definition. We defined the capacitor as a device that stores electric charge, and we defined the capacitance as the ratio of the charge on each plate to the potential difference across them. And we said 1 microfarad is equal to 10 minus 6 farad. We said the capacitance is proportional to what? To A, and it's inversely proportional to 1 over D. And we said that the capacitance is related to this by what? By permittivity times area divided by D. So let's move to arrangement of capacitors now. So we have 2 arrangements. We have the series arrangement and we have the parallel arrangement. We have the series arrangement and we have the parallel arrangement. So let's start with the series arrangement. When we say capacitors are arranged in series, what do we mean? Okay, so we have 2 capacitors, C1 and C2. C1 and C2. Don't forget, this is the symbol of a capacitor. This is C1 connected to what? To C2. When we say 2 capacitors are in series, what we're just trying to talk about is that we have a single wire connecting them together. As you can see here, we have 2 wires. We have 1 wire connecting both capacitors together. You can see we just have a single line here. They are joined together by a single line. So whenever you see this, we say that the capacitors are arranged in what? In series. So what is the equivalent what capacitance? What we want to do here is to calculate the equivalent capacitance. What we mean by equivalence is that what is the addition of these 2 capacitance? So what we do is we do 1 over C, where C is represented as the equivalent, must be equal to 1 over C1 plus 1 over C2. So we are adding the reciprocal of both capacitors together, and it must be equal to the reciprocal of the equivalent capacitor. So from here, we have 1 over C equivalent must give us the LCM of this C1 and C2 is going to give us C1, C2. So when we divide this by C1, that's C1, C2 divided by C1, we have C2 plus, and when we have C1, C2 divided by C2, we have C1. So that gives us that, or that tells us that 1 over C equivalent is equal to C2 plus C1, all divided by C1, C2. Permit me to write this like this. C1 plus C2 divided by C1, C2. So all I just did there was to I kept this C1 there and took that C2, but it doesn't change anything. We all know that 2 plus 5 is the same thing as what? 5 plus 2. It doesn't change anything. So from there, what I want to do from there is we want to find a value for the C equivalent. So one thing in maths we do is that if I have 1 over, let's say C is equal to 1 over 3, Take a look at what I have on the board. I have 1 over C is equal to 1 over 3. What this just implies is that it says that C is equal to 3. So what I just did is that if you take the reciprocal of 1 over C, you get C. But don't forget in math, whatever you do to the left-hand side, you have to do to the other side, which is the right-hand side. So I took the reciprocal of 1 over C, I got C, and I have to do likewise to the right-hand side. So if I take the reciprocal of 1 over 3, I get 3. Simply put, all you just have to do is, if we are like flipping this side, we also have to flip this side. So that approach is what I want to apply to this one now. So I want to bring C equivalence up, and the same thing happens to what I have here. So I can say that C equivalence is equal to, this one comes up now, and this guy goes down. So you can see that now. So for capacitors arranged in series, the C equivalence is equal to C1, C2 divided by C1 plus C2. You can see that, very simple. But this formula only applies for 2 capacitors. When we have more than 2 capacitors, then we have to apply a different means. We just have to go with this formula. When we have more than 2 capacitors, then we go with this formula. So I'm going to include this formula to part of our key topics today. 1 over C equivalent, or let me just write series, 1 over C1 plus 1 over C2. So you can see that this is for series arrangement. So let's move to parallel arrangement now. When they are arranged in parallel, what happens? Okay, so the first thing we are going to start with is that how do you identify capacitors when they are placed in parallel? Very simple. We have one capacitor now. Pay attention. We have one capacitor here, C1. We have another capacitor here, C2. You can see different wires. This capacitor 1 was connected across one wire. C2 was connected across a different wire. And then the 2 wires are joined together like this. They are joined together like this. And then we can now connect both ends to our circuit now. You can see, whenever you have something like this, they are connected in what? In parallel. So you can differentiate from this and this now. This one, we have a single wire. Whatever current flows through would flow through both. But for this one, it's like they are connected to 2 different wires, and those wires are connected together. They are interlocked together, and then they are connected to the what? To the circuit. Whenever we have something like this, it's very simple. All we just do is what? C parallel is equal to what? C1 plus C2. As simple as that. So you can see that this one is quite very simple. So when 2 capacitors are placed in, or they are put in parallel, or arranged in parallel, we just add both of them together. But when they are arranged in series, we have to use this formula to get our equivalent capacitance. So let's add these two, what we've done. So now let's take questions now. Let's take questions on what we've talked about today. So question 1. Question 1. Let me clean this off. If you have any question, just type in your question in our section. So we are going to get your question and we are going to give you answers to that. So let's take the first example. A capacitor of charge 5 times 10 to the power of minus 8 coulombs. So the capacitor, example 1. Just pay attention. Example 1, a capacitor of charge 5 times 10 to the power of minus 8 coulombs has a potential of 100 volts. It has a potential difference of 100 volts. So that question wants us to calculate the capacitance of the capacitor. The capacitance of the capacitor. So how do we do that? Very simple. Let's just go through our list of formulas. let's go through our list of formulas. We have Q, we have V. We want to calculate C. We want to calculate C. So from that first thing we wrote there, the first stuff we wrote there, we said that C is equal to, C is equal to Q over V, right? So from there, our C is equal to, don't forget that our Q is equal to 5 times 10 to the power of minus 8 coulombs divided by V, which is 100 volts. So this becomes 5 times 10 to the power of minus 8 divided by 100. And this gives us 5 times 10 to the power of minus 8 times 10 to the power of minus 2 farad. And this gives us a value of 5 times 10 to the power of minus 10 farad. So whenever you have stuff like this, for those of you writing JAMB, you know that you won't be permitted to use the scientific calculator. So all I just did there is just that if you have, 100 is 10 to the power of 2. So when you bring 10 to the power of 2 up, it becomes 10 to the power of minus 2. So that's how I got this line here. 5 times 10 to the power of minus 8. This is 100, which is 10 squared. So when you bring it up, it becomes 10 to the power of minus 2. And using our indices, 10 to the power of minus 8 times 10 to the power of minus 2. All you just need to do is what? Is to add up minus 8 and minus 2. And that gives you minus 10 farad. Very simple. Let me go through the question again. A capacitor has a charge of this and a potential difference volt of this. Calculate the capacitance. Simple. Just divide Q over V. Divide this with this and you get your answer. Very simple. So let's move to example 2 now. Example 2. Example 2 says that two capacitors of capacitance 5 microfarad and 3 microfarad are connected in series, and the resulting combination is connected across 600 volts. What is the equivalent capacitance of the combination? What is the equivalent capacitance of the combination? Don't forget that we have two capacitors. C1 is equal to 5 microfarad, and then C2 is equal to 3 microfarad. Don't forget they are connected in what? In series. They are connected in series. So the question said they are both connected to a supply of 600 volts. 600 volts. So the first question, high, is telling us to find the equivalence capacitance. So the question here is that when capacitors are arranged in series, how do you calculate the equivalence capacitance? Don't forget what we said that when they are arranged in series, we use 1 over C equivalent is equal to 1 over C1 plus 1 over what? C2. So that's what we're going to do now. So 1 over C is equal to 1 over 5 microfarad plus 1 over 3 microfarad. So we take the LCM. The LCM is 15. So 15 divided by 5 is going to give us 3 plus 15 divided by 3, 5 times 1 is going to give us 5. So all our results will be in microfarad. And from here, 1 over C equivalent is going to be 8 over 15 microfarad. And don't forget what I said, that whenever you have this in mass, you can just flip this. And whatever happens to this also happens to this. So our C equivalent now would be equal to, don't forget, I want to flip this now. 1 over CS is equal to 8 over 15 microfarad. So I flip this, so I need to flip this now. So I have 15 over 8 microfarad. So that is the answer for the first question. The first question says we should calculate the equivalent capacitance. Let me just go over that question again. We were given two capacitors, C1 and C2. We were given a voltage supply across them. We were also told that the two capacitors are connected in series. So the first question said we should calculate our equivalent capacitance. Since both of them are connected in series, all we just need to do is to use our formula here. That's 1 over Cs is equals to 1 over C1 plus 1 over C2. And that's what we did here. And we got 15 over 8 microfarad. So the second question says we should calculate the total charge in the combination. Permit me to rub this off. Total charge in the combination. So what's the symbol for total charge? So this formula comes to your mind. Capacitance is equal to Q over V. So from this first formula written here, C is equal to Q over V, we can deduce that Q is equal to C times V. And from there, we have our capacitance total, and we have V. So C equivalent is given as 15 over 8 microfarad, and then V is given as 600 volts. So how do we get out the charge now? How do we get the charge? Very simple. We just multiply the capacitance with the what? With the voltage. Therefore, Q is equal to 600 times 15 over 8 microfarad. So when we do this, 8 in 600 should give us 75. And then we have Q 75 times 15 microfarad. So when we multiply this, what do we have? Let's quickly do it here. 5 in 5 is 5, 2. 35 plus 2, 5, 7. And when we add this, we have 5, 2, 1, 1125. So that gives us 1125. So we have Q is equals to 1125 microfarad. So we can leave our answer like this, or we can write Q is equal to 1.125. Don't forget, all we just want to do is to write our answer in standard form. So that will be 1.125 times 10 to the power of 3 times, I told you that the value of the micro is 10 to the power of minus 6 farad. So when we combine this and this together, 3 minus 6, we have 1.125 times 10 to the power of minus 3 farad, and this gives us the final answer. Sorry, that should be coulomb. The unit of the quantity of charge is what? Is coulomb. So that is that. Let me just quickly go over it again. So the first question said we should calculate the effective capacitance, which we did. Don't forget they were connected in series. So we used our series combination, which is 1 over Cs is equals to 1 over C1 plus 1 over C2. So that was what we did here. So we took the LCM of 5 and 3. We got 15. So 15 in 5, 3. 15 in 3, 5. 3 plus 5 gave us 8 over 15. Then what I told you that if you are flipping this up, the same thing happens to this. So Cs is equal to 15 over 8 microfarad. So now we're done with question 1. The question 2 says we should calculate the quantity of charge. And don't forget, we said the quantity of charge is equal to the capacitance times the voltage. So Q is equal to CV. So all we just did is to multiply 15 over 8 together with 600 volts. And if you do that using your calculator, we get this. You get, don't be confused with what I did here. I was just trying to multiply this and this manually. But if you put this and multiply it with this on your calculator, you are going to arrive at this final answer. So let's take a look at the next question. So the next question says we should find the equivalent capacitance for two capacitors, 3 microfarad and 2 microfarad in parallel. So the 3 microfarad and 2 microfarad are in parallel, and they are connected in series with a 4 microfarad capacitance. So let's quickly do this. So we have C1 to be 3 microfarad, C2 to be 2 microfarad, connected in parallel, sorry. They are both connected in parallel. And then we have another capacitor, which is 4 microfarad. So this total combination is now connected in series with this guy now. Do you understand the question? Tactical question. 2 capacitors, 3 microfarad, 2 microfarad in parallel. Then they are both connected to this guy now in series. So the first thing we are going to do is what? Let's calculate the equivalent capacitance for this guy now. So for this guy, don't forget that when capacitors are in parallel, what do? Very simple. We just add them up together. So Cp is equal to C1 plus C2. That's the first thing we do. They are in parallel. So we use our parallel combination. You can just write this down somewhere. This is the highlight of everything we've talked about today. So Cp is equal to 5 microfarad. Sorry, that should be 3 microfarad plus 2 microfarad. And that's going to give us 5 microfarad. That's going to give us 5 microfarad. Then we were told that the whole combination is connected in series with this one now. So it is connected in series with the third capacitor, which is 4 microfarad. Series now. So how do we connect capacitors in series? We have 1 over Cs is equal to 1 over 5 microfarad plus 1 over 4 microfarad. So 1 over C series now is going to give us LCM would be what? 20. 20 in 5, 4 times 1, we have 4 plus 20 in 4, 5 times 1, we have what? We have 5. So 1 over is equal to 9 over 20. And finally, don't forget, we flip this one up. We do likewise here. And we have that Cs is equal to what? 20 over 9 microfarad. So the first thing we did was to what? Was to find the series combination of C1 and the parallel combination of C1 and C2. So we had them up. You understand? We had them up. We got 5 microfarad. So the 5 microfarad now is now connected in parallel, in series, with the 4 microfarad. So we use the series combination formula, which is 1 over Cs is equal to 1 over C1 plus 1 over C2, and we arrived at 20 over 9 microfarad. So let's take a look at them. The last objective for today, which is energy stored in a capacitor. Energy stored in a capacitor. Don't forget what I said. I said you should write this down somewhere. So when we move to the assessment questions, they will serve as lights to answering the questions. So energy stored in a capacitor. Very simple. W, which is equal to energy stored in a capacitor, is the product of the average potential difference, average PD, times the charge on each plate. On each plate. So the average PD is given as half over V. Since we have two voltage, the initial and the final voltage. So we have half V times what? Times Q. Therefore, the work done is equal to what? Half QV. So this is the formula for the work done by the capacitor. W is equal to half QV. But at times, they might just want to show a tactical one at you. They give you capacitance and voltage, and they tell you to find the work done. Very simple. Don't forget we said earlier that Q is equal to what? CV. So if Q is equal to CV, so if we have the C and if we have capacitance and voltage, we can just come in here and substitute our Q, and we have our work done to also be what? Half CV squared. So this will serve as the two formulas we're going to be using for our work done by a capacitor. So I'm going to add them to this list now. So W is equal to what? Half CV squared and W is equals to what? Half QV. So those formulas are what we're going to be using for what? For calculating the work done. So let's take a question on that now. A capacitor of capacitance 5 microfarad. So C is 5 microfarad. Is subjected to a potential difference of 1000 volts. 1000 volts across its terminals. Calculate the energy stored, W. Very simple. So we've been given C, we have V, we want to calculate W. So we are just going to use this formula here. Don't forget, W is equals to half CV squared because we have capacitance and what? And voltage. So let's quickly run through that. So we have half times what? 1000. Don't forget the voltage is squared. So 1000 times 1000 times 5 microfarad. So we have 2 here is 500. So we have 500 times 1000 times 5 microfarad. So 5 times 500 is going to give us 2500 times 1000 microfarad. And that's going to give us 2.5 times 10 to the power of 3 times 10 to the power of 3 microfarad. You going with me? JAM students, you need this. So this is times 10 to the power of 6 times our micro is given as what? 10 to the power of minus 6 farad. So what happens here? Something very funny happens here. 10 to the power of 6, 10 to the power of minus 6. What happens to them? They cancel out themselves. And then we finally have 2.5 joules. That would be in joules. Our work done is in what? Is in joules. So that's our answer, 2.5 joules. Let me just quickly run through that again. We have a capacitance of 5 microfarad. We have a voltage of 1000 volts. Calculate W. We use this formula here. W is equals to half CV squared. So we kept in all our parameters, C, V squared. So just press this on your calculator and then you are going to get 2.5 joules. Very simple. Okay. Okay, so we are going to go on a short break now. So when we come back, we are going to take your questions and then we give answers to them. So thank you for sending in your questions, and we'll try to go over all the questions and give you answers to the question. So, but before I move to the question section, I just want to quickly take a look at some of the things we talked about. So we started with definition of capacitors and capacitance. So we defined capacitors as devices that store electric charge. Then we said capacitance is the ratio of the quantity of charge across to the potential difference. Then we said 1 microfarad is equal to 10 to the power of minus 6 farad. We said the factors affecting capacitance are the area, the nature of the plates, and then the distance between the plates. And then we gave this important formula connecting these factors together. That C is equals to permittivity times area divided by D. And then we calculated the equivalent capacitance for series combination and for parallel combination. Then we rounded up the session with the energy stored in a capacitor by arriving at those two formulas for work done. So let's take a look at some of the questions we have. Demilade is asking how temperature affects capacitance. How does temperature affect capacitance? When we were looking at the components of the capacitors, we said that it is composed of two metallic plates. And we said one factor that affects the capacitance is the nature of the plates. The nature of the plates. So the effect temperature would have on capacitance is as a result of the effect of temperature on the nature of this plate. Do you get that, Demlade? What I'm just trying to say here is just that nature of the plates, that is the type of plates used in building the capacitor, is one of the factors. So the effect temperature would have on that material, you understand, now tells us the effects of temperature on the capacitance. So yes, to answer that question, temperature can affect the capacitance of a capacitor by changing the properties of the what? Of the metallic plate used. So Destiny wants to know the relationship between capacitors and resistors. Okay, fine. I am sure what Destiny is trying to drive at is that when we were calculating the series combination and the parallel combination of capacitors, we said that 1 over C in series, capacitors in series is equal to 1 over C1 plus what? Plus 1 over C2. So this is for what? For capacitors, yes. This formula is valid for capacitors. And we said that C parallel is equal to what? C1 plus what? C2. But for resistors now, for resistors, what happens is that the reverse is the case now. I'm sure that's what Destiny is trying to clear. The reverse is the case for resistors. We have C series is equal to what? C1 plus C2. And once C parallel is equal to what? 1 over C1 plus 1 over what? C2. But we ain't talking about resistors today. Our focus is on capacitors. But to just answer Destiny's question, you can see this. Series combination for resistors is C1 plus C2, while the series combination for capacitors is what? Is this. So the reverse is just the case. You get that? So if you know for one, you can just flip them back to get for the other one. And then another thing I'm going to add to that is just that when we're looking at AC circuits, then we're talking capacitors and what? And resistors. But when we're talking about what? DC circuit, that is currents that move in just one direction, then we focus on what? On resistors. Don't forget that capacitor and resistors are both components. Yes, they are both components. But capacitors store electric charges, while resistors, they resist. They oppose the flow of what? Currents. You get that? So that's the major difference between, I think I've given like 3 differences between both of them now. You get that? So this one would store electric charge. This one would oppose the flow of what? Current. And they are both used in what? In AC. But in DC, we make use of what? Of resistor. So I want to believe I answered your question, Destiny. So Favor is asking if we can apply Ohm's law. Yes, Favor. We can actually apply Ohm's law. But that will be for like for a further discussion on what? On capacitors. That's when we are talking about what? About AC circuits. Yes, when we talk about AC circuits. AC circuits. In AC circuits, we can have a combination of what? Of resistors, capacitors, and inductors. So when we have a combination of this, you understand, we talk about AC circuits. So yes, we can apply Ohm's law to capacitors too by saying that V is equal to what? IXC, where XC is the reactance due to the capacitor. But that's a different discussion. So this discussion is not for today's class. But yes, we can apply Ohm's law to capacitors too in a different dimension. So another question, Habe is asking if it's necessary to convert the microfarad to farad before substitution. Yes, Abe, if you feel that's more convenient for you, fine. So you can just convert the microfarads to farad before you resume by just using that what we said, that 1 microfarad is equal to what? 10 to the power of minus 6 farad. So you can just convert it to farad before you start, or you can use your microfarad in your calculation, but put it in your mind that what? Micro is to the power of 10 minus 6. But to make it, to avoid mistakes, you can just convert everything to what? To farad. Then you start with your what? You start with your calculations. Abe, I want to believe I answered your question. Abe is also asking, what is change? Okay, the change in denominator and numerator, what is it called? Yeah. So if you have 1 over C is equal to 1 over 3. Okay, how do you like put it mathematically? We can just say that taking the reciprocal of both sides, you can see that very easy, taking the reciprocal of both sides. So what happens is what? C becomes what? 3. That's one way of doing it. Very simple. Another way of doing it is that we can say that if we cross multiply, you get that? So we have C is equals to what? 3. Very simple. But you just have to state it. Cross multiply. So the examiner would know would know the method you are making use of. You can see. So happy. I want to believe that answers your question. So the name of the step, you taking reciprocal of both sides, very simple. I think this was the one I talked about during the lesson. Or you can just cross multiply. It also gives you that. So Destiny is asking, what is the live application of capacitors? Nice question. So capacitors, aside the fact that they store electric charges, you know, when I started the class, I said capacitors store electric charges. Aside from that, they are also using what? In AC circuits for rectification. What we mean by that is just that we can use them to what? To filter out DC. We can use them to regulate direct current so that we have a stable flow of what? Of current. We also use them in what? In signals. You get that? We also use them in signal cables. But their major use is what? Is for storing electric charge. So Sulaiman, I want to believe I've also answered your question. You are asking what are the uses of what? Capacitors. So I just said for filtering out DC, and I also said for storing electric charges. They are also using what? In signals, in time signals too. Yeah. So let's take a look at some of the questions we have here. Okay, so the first question is asking that a supply of 400 volts is connected across capacitors, 3 microfarad and 6 microfarad in series. Calculate the charge. So let's see if we can try this. A supply of 400 volts. Supply of 400 volts. V is 400 volts. Is connected across capacitors of 3 microfarad and 6 microfarad in series. These two are connected in series. So the question is telling us to calculate the charge. Calculate the charge. Okay. So how do we go about this? Very simple. The first thing we are going to do. Okay. So let me just give you a hint. I'm going to leave you to answer it. So the first thing you are expected to do is to what? Find the equivalence capacitance of these two. From there, now use this formula, the formula there, Q is equals to CV, to now get your quantity of charge. So I'll just give you like a minute to answer that question now. So if you have your answers, just like type it in the comment section. I'm waiting for your answers. So the first thing you're expected to do is to add them up. Okay, Abe got 800 coulombs. Okay, we are waiting for the rest. Okay, do we have other answers? Okay, Destiny also got 800 too. Okay. Okay. So Abe 800, Destiny 800. We are still waiting for your response. Okay, Peter, we just received your response too. Peter also got 800 coulombs. Wow, that's cool. Cool. Okay. Patrick got 800 coulombs too. That's fun. That's fine. London boy getting a different response, 80. He gave a different answer, 80. Okay. 800 coulombs too, praise. Okay, so Abe, Destiny, Peter, Patrick, London boy, praise. We have your response. So let's do it and see what we have. So 400 volts, we have 3 microfarad, 6 microfarad. So let's add them up together. Capacitors in series. This, okay, we have 1 over Cs is equal to 1 over 3 microfarad plus 1 over 6 microfarad. Yeah? Connection of capacitors in series. So from there we have 1 over Cx is equal to LCM of 3 and 6 is what? 6 microfarad. Don't forget that. So 6 in 3 is 2 plus what? 6 in 6 is 1 times 1. We have 1. And then we have 1 over Cs is equal to 3 over 6 microfarad. So since we have this, all we just need to do is what? Is to flip them up. So Cs becomes what? 6 over 3 microfarad. And that gives us 2 microfarad. So we have 2 microfarad. So our quantity of charge now is equal to CV. From the formula here, Q is equal to CV. And then we have our C as the 2 microfarad times 400 volts. So that will be 800 microcoulombs. I think that was the mistake a whole lot of us did. The answer should be 800 microcoulombs, and that should finally give us a value of 800 to the power of 10 to the power of minus 6 coulomb. And that is going to give us a value of 8 times 10 to the power of minus 4 coulombs. You forgot to convert your microfarads to what? To normal farad. So that was the mistake we did. So the answer is not 800. I think Abe is making a correction to his answer as yes, Abe, your answer is very correct. So let's move to the next question now. So how would the capacitance of a parallel plate capacitor be affected if the distance of separation of its plates is decreased? So if the distance of the plate is decreased, what effect would it have on the capacitance of a parallel plate capacitor? You have just 30 seconds to answer that. If the distance is decreased, what effect will it have on the capacitance? Okay. Waiting for your response. Okay, Abe is saying the capacitance would increase. The capacitance would increase. We have just 10 seconds left. We have 10 seconds left. Benedict is saying the capacitance would increase. Okay, thank you for your response. Destiny, we just received the response too. Okay, so because of time, so the answer to the question is if the distance of separation is decreased, the capacitance would increase. Don't forget we said that the capacitance from this statement here, the capacitance is inversely proportional to the distance. So whatever happens to the distance, the reverse happens to the capacitance. So if the distance is reduced, then the capacitance would increase. Thank you, Habe, Benedicta, and Destiny, for giving us the correct answer. So let's move on to the next question because of our time. So a parallel plate capacitor is charged and the charging battery subsequently disconnected. If the plates of the capacitor are moved further apart by means of insulating handles, what happens to the value of the capacitance? So we won't be answering this question because this question is very similar to the last one, all from last year. That's 2020 past question. You can see two same questions in the same year. So the answer to this question is just that if the distance are moved further apart, what happens to the capacitance now? It's going to what? Reduce now. You get that? The distance are moved further apart, the distance increases, so the capacitance would what? Would reduce. Very simple. The same question, the same year. Okay, so let's move to this question now. So which of the following statements about parallel plate capacitors is or are correct? 1. Capacitance of a capacitor is inversely proportional to the distance between the plates. 2. Capacitance can filter a signal from DC. And then the last one, capacitors can store charges. So is it A, 1 only, B, 1 and 2, C, 2 and 3 only, or D, 1, 2, and 3 only? You have just 20 seconds to send in your response. Okay, Abe gave a response. He said the correct option is D. That's 1, 2, 3. Okay, thank you, Abe. 1, 2, 3. Destiny said we have 1, 2, 3, 2. Thank you very much. Precious said the answer is B, 1 and 2 only. We have just 10 seconds left to give in to send in our answers. Peter said the answer is D. Okay. Emmanuel, thank you for your response. Emmanuel also picked D. Okay, let's just move straight on. So the answer to the question is D. You all are correct. So 1 is correct. Capacitance of a capacitor is inversely proportional to the distance, as said here. Then 2, they can also filter AC signals from DC, very correct, in AC circuits. Then they can also store charges. That's their main purpose. So 1, 2, 3, very correct. Thank you very much. So let's move on to the next. Okay, let's move on to the next question now. So this first question is telling us that what is dielectric? What is dielectric? Okay, a dielectric is just any material. A dielectric is just any material that can act as an insulator and is kept between two conductors. And kept between. Okay, so a dielectric is any material that acts as an insulator and is kept between two conductors. Yes, this question also came out, I think, 2017 or so. So I'll leave that calculation for you to do. So you can just send in your answers later. So let me just round up by going over everything we've talked about. So we started with the definition of capacitors and capacitance. So I said the capacitor is a device for storing electric charges. We also define the capacitance as the ratio of the quantity of charge to the what? To the potential difference across them. Very simple definition of this and this. Then I went ahead to give you the numerical value of the microfarad. I said 1 microfarad is equal to 10 to the power of minus 6 farads. Just write this. I want to believe we all wrote this down. So I also said factors affecting capacitance of a capacitor. Capacitance is directly proportional to what? To area. Whatever happens to area would happen to capacitance. If area increases, capacitance also increases. If area reduces, capacitance also reduces. Then I said capacitance is inversely proportional to the distance. So whatever happens to distance, the reverse happens to what? Capacitance. So as the distance increases, capacitance reduces. As distance reduces, capacitance increases. Then we connected the 3 factors by stating this formula that the capacitance is equal to permittivity, which is represented by epsilon, times the area divided by the distance across the plates. And then we went to the arrangement of capacitors. In series, we have this 1 over Cs is equals to 1 over C1 plus 1 over C2. And in parallel, just add the capacitors up. It gives you the equivalent capacitance. Then we rounded up with the energy stored in a capacitor. So the work done, the energy is equal to half CV squared, which is also synonymous to half QV, depending on the parameter you have. So that brings us to the end of this discussion. For more comments, for more contents on this topic, just click on Capacitor and Capacitance on the learnatom.ng website. So thanks for having you here. So join us again next week. Thank you.